Hello everyone, welcome to IMS GATE Academy. My dear friends, as you all know that we are running the most expected concept series on our YouTube platform, and I particularly am dealing with the heat transfer concepts. Till now 8 lectures we have completed as far as the heat transfer subject is concerned, and we have discussed about conduction in very much detail. In conduction, there are many topics from variable thermal conductivity to heat generation to generalized heat conduction equation to fins. We also have discussed about convection. In convection also I have discussed forced convection and free convection as well. Last class was about free convection. Today we are going to start with radiation basics, and this month, for this entire month, we will be in radiation, and the last one to finish it with heat exchangers, right. When the most expected concept series will be over, we will also solve some good questions based on the concepts that we have discussed. Okay. So my dear friends, today we will be dealing with basics of radiation, and all the radiation basics that we need to know will be discussed. Okay. So my dear friends, what is radiation? See, if I ask you what is the most basic difference between radiation and the previous two modes of heat transfer, that is conduction and convection, you will say simply that, sir, in the previous two modes we require a material medium for the transfer of heat, but in radiation we do not need any material medium. So that means radiation will always be there. So what are the good examples or the significance? The sun's rays that reaches earth, if radiation was not there, you can understand that it would become very difficult for us to survive. So that is perhaps the most important application. Then you all know that when you stand beside a bonfire, the heat that you get will be primarily due to radiation. So this is also there. Now my dear friends, when I talk about radiation, we know that no material medium is required. Okay, even if vacuum is there, then also radiation will take place, and it is based on one of the most basic laws of we can say physics. What? That any body, when it is above 0 Kelvin, that is the absolute temperature, it will radiate waves, it will radiate the radiation, and that is also known as Provost law. Provost law, that is called, that any material above 0 Kelvin it will radiate. Now how much is the quantity, that is depending on many factors, but it will radiate. Okay, this is one thing. Second, the related concepts with radiation will be electromagnetic waves, electromagnetic spectrum. Electromagnetic wave is a very broad term. I am not going into very much detail that how the experiment of electromagnetic wave and all is being conducted, but you know that it is a very broad term, and among that it will be thermal radiation, some part will be thermal radiation. Then electromagnetic wave is there, Planck's law is there. Then then throughout this radiation chapter we will be studying some very important laws which is governing the radiation. Then we will see the concept of black bodies, and after that we will also see that there are many related terms of energy. See, what is our objective? Our objective is that we need to know that, okay, when a body is emitting radiation, that what is the quantity that is being emitted. That is our objective. What are the laws that are governing that? On which factors it is depending, right? And then there are some related terms telling the energies radiated by the body. For example, what is emissive power, what is total emissive power, what is hemispherical emissive power, what is spectral emissive power, what is intensity of radiation. All these are telling you energies only, but how they are different from each other, that also we will see. Then what is the concept of view factor? Now probably view factor will come tomorrow. then what is intensity of radiation, right? So what are radiation networks, what are radiation shields? So all these important concepts that is there in radiation, all these things we will be discussing over here. Okay. Now my dear friends, now I will start with electromagnetic wave spectrum. Now you can clearly see that when you say electromagnetic wave spectrum, so many waves come over here, so many waves come over here. But before that, let me tell you some basic equations which are there in, for a wave, basic wave equations. So you know that C is equal to lambda into nu. Is it visible? C is equal to lambda into nu C is equal to lambda into nu, and also you know that E is equal to h nu. E is equal to h nu, you know this thing. So this is Planck's law. This is Planck's law. This is the concept of Planck's law. So I can also write, now what is C? C is the velocity of the wave in that medium, lambda is the wavelength, lambda is the wavelength, and this is the frequency, this is the frequency, and this is the velocity of the wave in medium, velocity of the wave in medium. Now generally this C is equal to the speed of light, that is 3 into 10 to the power 8 meter per second, and from these two equations what I can write, in place of nu I can write C by lambda. Now h is the Planck's constant, h is the Planck's constant, 6.624 into 10 to the power minus 34. C is also constant, so I can say E is inversely proportional to lambda. E is inversely proportional to lambda. So what is the significance? The significance is that when your lambda will be small, energy radiated will be very high, and that is why whose energy, the waves whose lambda is very low are considered to be more dangerous. For example, X-ray. For example, X-rays, how they are able to penetrate your, when you are going to do X-ray in hospital, how they are able to penetrate your bone and show the image inside the body, because they are having very high energy, and they are having very low wavelength as well. ठीक है. So entire spectrum you can see over here, and this is showing you the unit of wavelength over here is micrometer, and as you move up, the wavelength increases. So all the low wavelength rays will be down the picture. So clearly you can say X-ray, gamma ray, cosmic rays, they are having very low wavelength, and radio and TV waves will have very high wavelength. Now why I am showing you this picture? Not because I am teaching you electromagnetic wave, but because I want to show you where is the thermal radiation. We are not dealing with electromagnetic radiation, we want to know where does thermal radiation lies. So thermal radiation will lie over here. Thermal radiation will lie from wavelength of 10 to the power minus 1 to 10 square micrometer. From 10 to the power minus 1 to 10 square micrometer, and it will contain some ultraviolet part, some infrared part, some visible part. So this is the thing. Okay. Now my dear friends, see one thing, now we are going to study what is black body radiation. See, you know that any body above 0 Kelvin is going to emit radiation, okay, and it will depend on a lot of factors. For example, it will depend on temperature also, it will depend on the the material itself also. It is not that I have kept two bodies and at the same temperature they will emit the same energy. It is not like that. It will depend on a lot of factors. Wavelength it will depend, temperature it will depend, material itself it will depend. So there is a need for a body that I know that at a particular temperature this body will emit the maximum radiation, so that it is useful for comparison purposes. Like in thermodynamics, you consider Carnot cycle for just for comparison, that you know that it will be having a highest efficiency, so we can use for comparison. Here also there is a body which is used for comparison purposes, and that body is known as black body. So what is this? The first term that we are introducing, what is black body? What is black body? So it is a perfect emitter, or I can say perfect absorber, then it is an ideal emitter. Ideal emitter, always remember three things about black bodies: perfect absorber, ideal emitter, and diffuse in nature. And diffuse in nature. So what is perfect ideal emitter? Ideal emitter means that at a given temperature it will emit the maximum energy. Maximum energy it will be emitted. Now what is the quantity of that we will discuss a bit later, but you know that it will be emitting maximum. Perfect absorber means what? It will absorb everything, and by common sense also we know that a black colored body, it absorbs almost everything, right? So that also we know. And diffuse in nature. What is diffuse in nature? See, actually for a real body with direction, the quantity of energy radiated changes. So black body is such a body that in any direction whatever energy it will radiate, it will be having same magnitude. And this I have given you over here, that see, if you have kept a black body, so from the top surface it is emitting. Now first of all, it is emitting in a hemispherical direction. That's why in all the terms you will find hemispherical term. Why? Because when it emits above, it forms a hemispherical kind of, that means in every point, in every direction it is emitting, okay. And it is, all the lines are having the same length. It means it is diffuse in nature. Diffuse means in every direction the magnitude is same, okay. Now I will also tell you that radiation is generally a volumetric phenomenon. It is taking place throughout the volume, but most of the bodies are opaque in nature. The bodies that we deal over here in our thermal radiation, it is opaque in nature. When it is opaque, whatever is radiated gets absorbed within the body. That's why the rays which are coming out from the top surface, that only is worth discussion. That is only we are seeing. So for opaque bodies we will say that it is a surface phenomenon, but for all it's a volumetric phenomenon, okay. So what is the black body? Perfect absorber, ideal emitter, diffusive in nature. Now my dear friends, there must be some term which is used for telling you the power, energy emitted for a black body or for any body, but first let us discuss about what is the black body radiation, okay. So what is total hemispherical emissive power? So the energy, the radiation energy which is emitted from the body per unit surface area, per unit time at a particular temperature is called the total hemispherical emissive power. Now why he is giving total? Total means considering all the wavelength. At a particular, the energy which is radiated by a body, it keeps on changing with wavelength. So now he is using the term total, that means considering all the wavelength, number one. Number two, hemispherical. Why it is hemispherical? I already told you that when the body, when a surface radiates it, it will be from the top surface. That's why top surface, and that too in hemispherical, the region forming over the surface will be hemispherical in nature. That's why hemispherical. Emissive power. Emissive power. So energy means the total energy emitted, okay, joule, per unit area, meter square, per unit time, second. So joule per second is watt per meter square. So this is the unit for total hemispherical emissive power. Total hemispherical emissive power. I am again saying the definition: total energy emitted per unit surface area, okay, per unit time, okay, for all the wavelength, that means integrated all the wavelength. That's why he is using the term total, is known as total hemispherical emissive power. Total hemispherical emissive power, okay. It is denoted by EB. Now since we are discussing for a black body, I have to write here B, okay, and it is given by, this energy itself is given by the Stephen-Boltzmann law. The Stephen-Boltzmann law, that is the most important law in the entire, I can say which is, I will not say most important, but the most used law in the entire radiation, in entire thermal radiation, is nothing but giving you the total hemispherical emissive power, sigma T to the power 4, Stephen-Boltzmann constant, 5.67 into 10 to the power minus 8. T is the absolute temperature in Kelvin, absolute temperature in Kelvin, and C, it is depending on the fourth power of the temperature. It is depending on the fourth power of the temperature, so proportional to T to the power 4, sigma T to the power 4. It is nothing but for black body, nothing but for black body, okay, nothing but for black body. So if someone asks you what is the unit of sigma, what is the unit of sigma? So EB, it is watt per meter square, and T to the power 4, that means Kelvin to the power 4. So this is the unit of sigma. This is the unit of sigma. What is the unit of sigma? Watt per meter square, Kelvin to the power 4. This is the unit of sigma, okay. So EB equal to sigma T to the power 4. Now my dear friends, there is a word total emissivity. You know that the energy that I gave you, that was for black body, but all the bodies are not black in nature, some are non-black also, and mind it, the word I am saying that it is black, not necessarily the color is black, not necessarily the color is black, not necessarily the color is black. It is due to the nature that we are saying black body. See iceberg, that is in Antarctica, snow, that is also considered as a very good idealized black body. Why? Because it absorbs all the sun's rays, and that is why in the news you will always see that icebergs are melting, sea level rising, all these things you will hear in the news. That means what? Snow is a very good black body. So not necessarily the color is black and we are saying black body, okay. So what about for non-black bodies? For non-black body, this term is coming into picture, which is the total emissivity. So consider a non-black body is there at a temperature T. This is a non-black body, and consider a black body is there. This is a black body, also at a temperature T. So it will emit how much? Let's say EB, and this is emitting, let's say E, and you know that at any temperature black body will emit maximum, So definitely E is less than EB, definitely E is less than EB. So the ratio of E and EB is called total emissivity. Obviously, it is unitless, and remember that it is at a given temperature. At a single temperature we are talking about this thing. At a single temperature we are talking about, at a given temperature we are talking about this thing. Also one more thing, epsilon, this is epsilon, this is epsilon, okay. Epsilon varies with temperature, it varies with wavelength also. Epsilon is not constant. If you think that it is constant, no, it is not constant, it keeps changing with wavelength, temperature. Remember, wavelength and temperature are very important parameters when it comes to radiation, and the properties keeps on changing when you vary those things, okay. Obviously, for numerical purposes we don't consider all those variations, we keep it as simple as possible, but you should know that it is changing, okay. Now my dear friends, there is a term monochromatic emissive power. What is monochromatic? Whenever monochromatic comes, you know that we are talking about per unit wavelength. Whatever energy or emissivity we are discussing, that was for all the wavelengths. That was for all the wavelengths. For example, the first term, what was the first term? Total hemispherical emissive power. That was for all the wavelengths, but now I am saying monochromatic emissive power. When I am saying monochromatic, it is for per unit wavelength. That means now we are interested energy radiated by the body at a given temperature, but for a given wavelength or per unit wavelength, and then only we will say that it is a monochromatic. That means it is denoted by E lambda. E lambda, that means energy emitted per unit wavelength. So just imagine that I am able to get E lambda, and here is the lambda. On the x axis there is lambda, on the y axis there is E lambda, and some kind of curve we have obtained for at a given temperature. This is the kind of curve that we have obtained. Now what is the benefit of E lambda? What is the benefit? The benefit is, once you know the curve, so let's say this is your lambda 1 part, let's say this is lambda 1, this is lambda 2. For example, this is the energy E lambda 1 at lambda, this is the energy at lambda 1, and this is the energy at lambda 2. So when we are interested in knowing the energies between, total energy emitted between lambda 1 and lambda 2, I can find this area by integration and get the total energy between lambda 1 and lambda 2. So what is the benefit? The benefit is that once I know E lambda curve, and this is d lambda, and when I integrate between lambda 1 to lambda 2, I get the total energy emitted between a particular given wavelength. So that means what? That means I am not every time I am interested in knowing the total energy emitted between for all the wavelengths. Sometimes I am interested to know the energy between two wavelengths also. This is the significance of monochromatic emissive power. Sometimes it is also known as spectral emissive power. Spectral. Okay. My dear friends, similar concept is of monochromatic emissivity. Total emissivity was E by EB, but that was for all the wavelength. And now when I am discussing about a particular wavelength part, then comes monochromatic emissivity. Monochromatic emissivity is epsilon but for lambda. So that is nothing but for a non-black body E at a given lambda divided by for black body but at a given lambda. So always remember that whenever spectral or monochromatic comes, we are talking about with respect to lambda. Okay. Now there is a, so you note that now for with lambda this E will change, the energies will keep changing with respect to lambda. Okay. So you will have many emissivities, epsilon lambda 1, epsilon lambda 2. You have for a simple body, you will have at lambda 1, then epsilon at lambda 2, then you will have epsilon at lambda 3, and so on. You will have many epsilons. So that body whose epsilon at any lambda is equal to the total emissivity, that body is known as your gray body. So what is a gray body? Gray body is such a body whose emissivity is not dependent on lambda, it is same irrespective of the wavelength. Okay. So gray body clear, black body it's clear. Okay. So all these terms are very much important. These are the basic terms and it's very much important to get a clear idea of those terms. So once again, what are the terms that we discussed? The terms that we discussed are total hemispherical emissive power, number 1, then total emissivity, number 2, then spectral emissive power, number 3, spectral emissivity, number 4. Okay. Now my dear friends, let us discuss absorptivity, reflectivity and transmissivity. Okay. These are some of the basic terms. It's very basic in nature, not necessarily for a black body, it's for all the bodies that I am talking, any general body that we are talking about. Okay. Let's say that let's say this is the body and here is some 100 units of energy that is incident. So when it is incident, now no matter whatever the type of body will be, some part will be reflected. Let's say 25 units is reflected. Some part will be absorbed within the body. Let's say 50 units is being absorbed within the body, and some will be transmitted also. Some will be transmitted also. So 25 unit is transmitted. So you add this, you get 100. So the fraction of energy which is absorbed by the body is known as absorptivity. And how much fraction, how much energy is absorbed? 50 units divided by total energy is 100. So it is 0.5. Okay. Some part is reflected also. How much is reflected? 25 by 100. Fraction of energy reflected is known as reflectivity and it is 0.25. It is 0.25. And the part of energy which is transmitted, that is it is also 0.25. Okay, how much is transmitted? 25 is being unit is transmitted. So obviously you can see that alpha plus rho plus tau is equal to 1. Okay. Now you know that alpha plus rho plus tau is equal to 1 for any body. So mostly what happens in our thermal radiation, we will deal with opaque bodies. We will deal with opaque bodies. So for opaque bodies, that means it will not allow any part of energy to go through it. So when it is opaque, tau will be 0. When tau will be 0, I can say that alpha plus rho is equal to 1. Similarly for black body, alpha, it absorbs everything, so alpha will be 1. It absorbs everything. Similarly for white bodies, rho will be 1. All these things are there. Very important to know that all these properties alpha, gamma, alpha, tau and rho, they keep changing with temperature, they keep changing with wavelength. It is not that it is constant for a particular at a particular wavelength or temperature and it will be same throughout. No, it will keep changing with respect to wavelength. The very good example I am giving you, in summer season you are visiting, let us say, a mall, or you are going for a movie with your family. You have parked your car outside the theatre, you went for the movie, you watched for 3 hours, you came out, and then you will see, when you will go, you will close all the windows. So when you will come, when you hesitate to go inside, when you open the door, you will find suddenly so much of heat there trapped inside the car. How is that possible? How is that possible? See, when you are closing the window panes, whatever rays are being striking the window, they are initially at shorter wavelength, and when they are at shorter wavelength, the glass panes are allowing it to pass through it, and when it passes through the glass panes, it will undergo many rounds of reflection and ultimately its wavelength will be increased. When its wavelength will be increased, the glass panes will become opaque in nature. That means initially for the shorter wavelength it was acting in a transparent manner, but when it will, the wavelengths have become larger, greater after several rounds of reflection, the same window pane will act as a opaque surface, and when it will become opaque, it will not allow it waves to pass through it, rays to pass through it, and that's why the heat gets trapped, and that's why you feel very hot. One of the life saving phenomenon that takes place, or that incurs, or that consists about these like phenomenon, short wavelength and long wavelength, is the greenhouse effect. The greenhouse effect takes place based on the same conditions. When the sun rays comes in our atmosphere, the atmosphere acts as very transparent, it allows, but the same when the rays strikes the earth's surface, the wavelength increases. When the wavelength increases, the same atmosphere acts as an opaque surface, it does not allow the ray to go. So that means heat is trapped, and we feel that for survival heat is very much necessary. Not excessive heat, but heat is necessary. So this is the phenomenon of greenhouse effect. So that is what we want to prove, that alpha, all these properties are there, they are dependent on wavelength, temperature and other factors as well. Okay. Now my dear friends, all these basics, after studying all these basics, now we are here to learn all the basic phenomena or basic laws that are governing your thermal radiation. First is Kirchhoff's law. What is Kirchhoff's law? Now, not for the electrical one, in electrical also Kirchhoff's law is there, not that one. For the radiation, what Kirchhoff has said, that suppose an enclosure is there, and you have kept a body over here. Now for this body, initially they might be at a different temperature, but after equilibrium, once they have maintained the thermal equilibrium, this body and the enclosure, thermal equilibrium is same temperature. Okay. When they are in thermal equilibrium with each other, so for the same body, that means at thermal equilibrium, its alpha will be equal to its emissivity. Its alpha will be equal to emissivity. That means how much is the alpha? Absorptivity is equal to its emissivity. And somewhat it is telling you about the nature of the black body as well. How? Because for black body, alpha is the highest. So when it absorbs everything, and it is having high alpha, so it will have high emissivity also, and you know that at a given temperature a black body emits the highest. So more alpha, more emissivity, it complies, it is in conjunction with the, it agrees well with the black body concept also. Okay. Where will this come into use? Later part, when we will discuss about radiation networks, then I will make use of alpha is equal to this concept. Okay. Planck's law of thermal radiation, and perhaps is the most important law in your in our thermal radiation, this is the most important law. Okay, what is Planck's law? First of all, it gives you, now from here, there are three laws that we will study back to back. First is Planck's law, then is Wien's law, Wien's displacement law, and then there is Stefan-Boltzmann law. Yes, we have studied Stefan-Boltzmann law, but let's say again I will tell you. These three laws are only for black body law, number one. Kirchhoff law for any body, these three laws for black body. So now black body. Now Planck's law tells you about EB lambda. Why I am writing B? Because black body. Why I am writing lambda? Because it is telling you about spectral emissive power. Spectral, that means at a particular, that means it is for, when I am saying spectral, it is for at a particular wavelength. That means EB lambda is at a particular temperature and wavelength. So EB lambda. Now I am writing the expression that is given. So the expression is C1 by e to the power C2 by lambda T minus 1. And when it is spectral, so watt per meter square, micrometer per unit wavelength. Okay. So C1 and C2 are constants. I am not writing what are the constant values. You need not memorize it. But just you see that it is giving you the relationship with EB lambda and lambda. EB lambda versus lambda at a given temperature. EB lambda versus lambda at a given temperature. This is the Planck's law. Tells you about the black bodies, and EB lambda is the spectral emissive power. Spectral or monochromatic? Spectral emissive power. Okay. So when you have the equation of EB lambda and lambda, can you plot a curve at a given temperature? Yes. And when we plot a curve, it will be something like this. EB lambda is there, lambda is on the x-axis. When you plot the curve at a given temperature, it will look something like this. Okay. Now this picture I have taken from Sengel in case you want to know. So what are the notable features over here? The notable things are that first of all, it is a continuous function. EB lambda is a continuous function, not broken somewhere. It is a continuous function of with respect to lambda, number one. Number two, if you consider at a given temperature, if you fixed at a given temperature, what you are seeing? You are seeing that EB lambda first increases, goes to a highest and then decreases. This nature can be very well said. Okay. Now notice the peaks. When you increase the temperature, the peaks move towards the left side. That means majority of the radiation is taking place at a shorter wavelength only. When you are increasing the temperature, all that means more than 50% is occurring before only. At shorter wavelength only maximum radiation is taking place. Okay. Now see, this is the for a given temperature, all these curves are being plotted. So T, you know. I am interested to know that where is the, at what wavelength is the peak coming. I am interested to know that you can clearly see the peak of all the wavelength. Okay, at every temperature, different curves are there. I am interested to know that at what wavelength these peaks are coming, and that is when lambda into T is constant, and that constant is given by 2897.8 micrometer Kelvin. So this is nothing but your lambda T max. Lambda T max. Why I am writing max? Because lambda, at lambda maximum highest energy we are getting into that particular temperature, lambda into T is equal to this constant, and this law is nothing but the Wien's displacement law, Wien's displacement law. Okay. So this is Planck's law. This is Planck's law. This particular law is Planck's law. What it tells you? It tells you, it gives you the graph between, or it gives you the relation between spectral emissive power versus lambda for a black body at a given temperature. Okay. And then you are interested, you know the temperature, and you are interested to know that what is the lambda at which the peak is coming. What is the lambda at which the peak is coming? So I know the temperature already, I know this right hand side value, I can find the lambda. This relation is known as Wien's displacement law, and that is our second law, that is Wien's law, and that is also for a black body. That is also for a black body, right? Now my dear friends, you know what is Stephen-Boltzmann law. Still I am saying how it is coming. See, from Planck's law I already know what is EB lambda, right? D lambda I know, and when I integrate between 0 to infinity, that means for all the wavelength, when I integrate, I will get EB, and that is nothing but sigma T to the power 4, which is the Stephen-Boltzmann law that we all know. How it is coming, that I told you. And what is EB lambda? The bigger expression of Planck's law that I have written earlier. So here the question comes that among the three laws, which is the most important, Planck's law or Wien's law or Stephen-Boltzmann? So the answer is Planck's law. Why? Because the Planck's law, when you differentiate the function, you will get Wien's law. Now why I am saying differentiate the function? Because suppose that I have given you a curve and I am asking you that where the maxima or minimum point is there. So what do? You differentiate, and when you differentiate you get the lambda. Okay, so when I differentiate I will get Wien's law. When you integrate you get the Stephen-Boltzmann law, and that is your Stephen-Boltzmann law. So very easily you can say that the most important law is the Planck's law over here, because from here only the remaining two laws are coming. And the second thing, all the three laws are applicable for a black body only. See, I have written B. In all the expressions I have written B. So it is for a black body only. So suppose that I know the energy for a black body. So how can I get for a non-black body? This is for a black body, watt per meter square. So for a non-black body, you know there is a term total emissivity. So E is equal to emissivity into EB, that is emissivity sigma T to the power 4, and unit will be watt per meter square. So for a non-black body I know this is the energy. So till now I told you that what is our objective? Our objective is that I know that energy is being radiated, but what is the quantity? I have got the quantity. And mind it, it is not for all the temperatures, it is for a particular temperature. In radiation, whatever laws we are studying, that is for a particular temperature only. So you put the temperature over here, you get the total hemispherical emissive power. Okay. So all these things are there. Now my dear friends, see, I will just give you an idea about what is radiation intensity, and then we will continue from tomorrow. See, in general what happens for any real body with direction, the magnitude of energy radiated varies. Then you will say that, sir, just now you told that it is not vary, you showed a diagram where it was same. That was for a black body. For a black body it is diffuse in nature, it is not dependent with direction. It is the meaning of diffuse body. Diffuse body, that means magnitude or intensity of radiation is same in all the direction. The term intensity of radiation is used for when we are giving energy in a particular direction. Then the term intensity of radiation comes into picture, and that is different for a non-black body but same for a black body. That is why you will see a very good hemisphere for black body, but for non-black body you will, the arrows are very non-uniform. So this intensity of radiation will be used for a non-black body. Okay. For black body also it will be used, but that is simple. In examination you can expect question based on black body only, non-black body generally will not come. Okay. So with change in direction, the intensity of radiation changes. That is why the concept of radiation intensity comes into picture. Okay. Now when we are talking about direction, we must know how to define a direction. We must have a coordinates to define a direction. See, when you are saying radiation, all these things are vectors only. Radiations, waves, all these things are vectors only. When it is vector, you need to know direction. Without direction, you cannot proceed. So you have three systems: Cartesian coordinates, cylindrical coordinates, spherical coordinates. It is very suitably can be expressed in terms of spherical coordinates, and that is why I have showed you the picture. Again, it is taken from Sengel. The picture that I am showing you, it is showing a vector kind of thing. This is the, let us say a one ray, it is going out. Now see, very conveniently it is being expressed with respect to z, theta and phi. So in spherical there is z, theta and phi. Predominantly theta and phi only can do. Now z is the height, z is the height of this point, z is the height of this point. Now this theta is called the zenith angle. This theta is called the zenith angle. What is zenith angle? This angle which is making with respect to z axis, that is the zenith angle. And this ray, when you take the projection on the xy plane, and then the angle that it makes with the x axis, that is known as azimuthal angle. That is known as azimuthal angle. And z is the height, the perpendicular height of the point with respect to xy plane. Okay. So using z, theta and phi, you can very easily tell that, okay, this is the direction that we are talking about. So spherical coordinates we will use. Why we will use? Why this is needed? Because with change in theta, actually this term radiation intensity tells you that how the rays or the magnitude is changing with respect to the theta. That is the main objective. So this is the concept of radiation intensity. Okay. So as of now I am keeping it till here. Why? Because from here I need to explain the concept of solid angle, and then all these things, we are going to develop a good term. All these things, the more in-depth analysis that we will do in tomorrow's lecture. So today only the basics part I have covered, the basic terms I have covered. I will again tell you the what is the summary of today's session. So today we have seen only the important terms, like what is the total hemispherical emissive power, then what is the emissivity, what is the spectral emissive power, what is the spectral emissivity, all the laws, Planck's law, then Kirchhoff's law, then we have seen Wien's law, then Stephen-Boltzmann law, and then finally we have seen the radiation intensity concept. What is radiation intensity? I have told you. We are going to make use of spherical coordinates, that also I have told you. What are the things that I have told you, and tomorrow we will take up from here. Okay, and slowly you will see that how we are going into the concept of view factor. Why I have started this, why I need to tell radiation intensity? Because we are slowly going, this will lead us to the concept of view factor. Now view factor will come into picture. So tomorrow class I will be discussing about this solid angle. Yes, solid angle concept will also come into picture. What is solid angle? What is the concept of solid angle? So all these things will come into picture. And secondly, what is view factor? That also we are going to discuss in detail. So tomorrow's class, these two terms will be very much discussed in detail. So don't miss tomorrow's class. As of now I am keeping it till here. For any doubts you can leave it in the comment section. Okay. So thank you class. Thank you all.